Review for quiz 3, part 2, the last 5 questions. Question number 6. Now, smooth function, another question. So let us use the same method to prove it. Yeah. This time, our f of n equals n to the nth power. Okay? Much more complicated. So we want to show this function does not belong to big theta of, not this one. Yeah. To show it's a smooth function, we want to show f of 2n does not belong to big theta of n to the nth. Yeah. Okay? Yeah. This time, first, let's look at the form of f of 2n. This one, right? Yeah. But we need to simplify it. Okay? It is not easy to see clearly how large it is. Yeah. So let us write in this way. We split to the base 2n to 2 and n. Okay. Exponent 2n here, 2n here. Okay? Yeah. That is by the property of exponential functions. Yeah. Then, the first part, 4 to the n, right? Second part, n to the still 2n. Yeah. Because we cannot make it more, make it simpler than that. All right, so that is the current form. Now compare f of 2n, f of n. We like to look at the limit. F of n over f of 2n. Okay. Limit n to the nth over 4 to the nth times n to the 2n, right? See? Yeah. Then, after simplification, you can see numerator 1, denominator very big. It is very easy to see this limit equal to 0. So then you cannot say, because not belong to, so you can easily see f of 2n does not belong to big theta of n to the nth. Yeah. All right, so that's question number 6. Number 7. All right, covered, yeah. All right, number 7, golden ratio. Which are following golden ratio root of quadratic equation? So we know that, right? Yeah. We know that phi squared minus phi minus 1 equal to 0. Okay. So this is the basic equation for the golden ratio. Yeah. We rely on this equation. Yeah. You can see in many questions when we need to simplify the expressions involving golden ratio, we need to use this equation. Yeah. All right. Next, linear combination concept. Linear combination concept. In one of the videos, when I explained the procedure how to solve second order linear recurrence relation, homogeneous linear recurrence relation, I use this concept, linear combination concept. Okay, yeah. So here in the option, ax times by, linear. So you do not have non-linear term. Okay. in each of the remaining options, you can find a nonlinear term. Option A, by squared, it's a nonlinear term. Y squared, nonlinear. Option B, ax squared, nonlinear term. Both nonlinear term. So the answer C, correct. It is a simple concept, but in that video, we try to find the solution for that second order homogeneous linear recurrence relation. This concept plays critical role. Critical, yeah, very important. Otherwise, we cannot get the general solution. We have two special solutions. We want to combine two special solutions. Combine to get one general solution. How do we combine? Linear combination way to combine. So you can see its role is very critical. Yeah. All right, so the next question. Yeah, this one. We want to make this phi to the nth power to a phi plus b form, yeah, for some integer a and a b, not necessarily positive. A integer and a b integer to represent any phi to the nth expression. Yeah. The answer is true. The answer is true. But if you want to convince yourself, you need to phi to the nth can be represented as a phi plus b. Yeah. Because for many students, you may feel it is hard to get it. Yeah, get this linear expression. It is very hard. But remember, we have this property for the golden ratio. When you have this property, you can always bring down the degree of your expression by 1 every time you do this kind of substitution. You can write in this way. Right? The first. First, phi plus 1. Right? Yeah. After that, you simplify a little bit. All right? Do you just bring down the highest term? It's order by 1, right? It's degree by 1. Okay? So every time you do one substitution in this way, you reduce the degree by 1. Then you keep doing reduction, degree reduction. Keep doing that. And you have to stop at the end, right? So when you reach the a phi plus b form, you have to stop because you can never find a phi square term. When you can see a phi square term, you can bring down the degree by 1. But if you never have that phi square term, you have to stop. Yeah. So if you use that way, you can convince yourself. You can do that. All right. The last question, similar to this one, but we change to phi to the n. Yeah. So you have different ways to view. You can do the same thing here. But here, I like to use one special way. This 1 over phi to the n. Can we write 1 over phi to the nth? Yes, we can. All right. let us just do 1 over phi first. 1 over phi equals, we know, 1 equals phi squared minus phi, right? Yeah. So phi squared minus phi over phi. We can do cancellation. After cancellation, we get a phi minus 1. That's 1 over phi. This time, 1 over phi to the n equals phi minus 1 to the nth. Okay, so you can see this side completely a polynomial of degree n, highest order, highest degree term n. Can you use the question number 9? Replace every time you see a term with degree greater or equal to 2, you can bring down by 1. So in this way, we can do that degree reduction, the same procedure, again and again. Finally, we can bring it down. We can get to the A phi plus B form. Okay, yeah. So this way, here, I do not need you to give a proof. Okay, just use some reasonable logic to convince yourself it is correct. Okay, all right. So that's the part 2.